Hello everyone, this is Michael. Welcome to a video on three-phase configuration and calculation with sample exercise. At the end of this video, we will have a sample exercise for you to practice on, so stick around. To understand about three-phase configuration, we need to go back to the basics first. How a basic single-phase AC generator and a three-phase AC generator works. Now we have a permanent magnet here as our field, and our coil here as our armature. What is represented here are two coils, but actually this is one coil winded around our field. Now when this magnet turns, this would happen. As the field rotates closer to the coil, the induced voltage also increases, thus this waveform is presented. Now, when the north is directly perpendicular to the coil, the induced voltage is at its maximum. And as it moves away from the coil, the induced voltage also drops down until it goes to zero. Now, this negative sine wave is the indication that this north side of the magnetic field is now on this side. That is why we have the negative swing here. And as it rotates further, it goes to this coil again. So the cycle continues until it is stopped. That is for the single phase. Let's go to the three phase. In a three-phase system, there are now three identical coils, and they are arranged 120 degrees apart. 360 divided by 3 is 120 degrees. Now as the field rotates, each of these coils here produces their own sine wave. Now the sine wave that would be shown here would be color-coded so as not to complicate the three waveforms that is being produced. As the field passes through each coil produces its own waveform. Now since they are 120 degrees apart, as the first coil produces its own waveform, 120 degrees later, another coil produces its own waveform. And so with the green waveform. Now there are three types of configuration. Basically there are two. But for the Y configuration, we have the neutral. So for Y, it is called Y because it simply looks like a Y configuration. So one of the sides of the coils are connected together. On the Y configuration with neutral, we have a neutral connection to each of the coils. While in delta, we have this configuration. Now it is important to be familiar with the terminologies and the parameters, electrical parameters of a three-phase connection, specifically for Y and delta. Now for a Y connection, we have the phase voltage. The phase voltage is the voltage that could be measured across each of the coil. So each of the coils here have its phase voltage. So if the phase voltage of this coil is 100, then the rest would be 100 because they are identical. That is the phase voltage. We call it phase voltage. Next is the line voltage. Line voltage is where you measure across each of two of the three lines of a generator. You can measure line voltage across line 1 and line 2, line voltage across line 2 and line 3, and line voltage across line 1 and line 3. So we call that VL, or line voltage. And next is the current. The current is the current that flows through each of the phase here. We call it the phase current. So if we have a phase current through this coil, we also have a phase current through this and this. So phase current, because it is the phase that the current that flows through each of the coils. We call it phase current. Next is the line current. Line current is the current that is drawn out of the generator. So outside connection of the generator is the line current. We call it line current. Now, to understand the relationship between phase voltage and line voltage, we need to examine where is the line voltage connected with respect to the phase voltage. So what is the relationship between the line voltage and the phase voltage? So here, for example, we take into consideration line 1 and line 2. So we measure the line voltage across line 1 and line 2. But looking inside the generator, we connect line voltage to this node here and to this node here. In other words, the line voltage is the combination of the voltage that is developed across these two coils here. So if we examine it by common sense, we should say that the line voltage is greater than our phase voltage, because it is now the combination of the two phases or two coils. So we can say then that the line voltage is greater than the phase voltage. Now, at what extent is line voltage greater than phase voltage? We need to remember a factor here which we can use for the rest of the formula for y and delta. Remember, factor of square root of 3. Now, since we learned that line voltage is greater than phase voltage, we can say then that VL, or the line voltage, is equal to the phase voltage times the factor, as I said earlier, the factor square root of 3. That is the relationship between line voltage and phase voltage. How about the phase voltage in terms of line voltage? We have VL divided by square root of 3. Again, since VL is greater than the phase voltage. The next is the relationship between current. We have IL and IP, or line current and phase current. So if we examine again, what is the relationship between line current and phase current and line current? So where does this line current came from? So if we'll take a look inside, where is it generated? We can say that this line current is coming from this phase current here. Also, this phase current is flowing through this line current here, the same as through this here. So by just examining by common sense, line current here is the same current that is drawn from the phase current. Why the same? Because we don't see any node here that would divide our current. So therefore, phase current is equal to the line current. We can say then that the line current is equal to the phase current. That is our basic formula for Y configuration. Now let's go to the delta configuration. We'll be talking the same about terminologies with Y configuration. We have the phase voltage, the voltage across each of the phases here. We call it phase voltage. We have the line voltage, the voltage that is measured on any two of the three lines outside of the generator. And we have the phase current, the current that is developed, induced across each of the coils or each of the phase. And the line current, the current that is delivered outside or through the line of a generator. Now again, what is the relationship between line voltage and phase voltage for delta? So the line voltage is measured either two of the three. So if we take, for example, the line voltage across line 1 and line 2, and if we trace the connection between line 1 and line 2 inside our generator, we would say that the line voltage is connected to this point here and to this point here, or in other words, it is directly parallel to this phase here. So this voltage here measured here and here would be the same voltage that is measured across this phase. Now you might be talking, how about the voltage across here? In any network, if one device is connected in parallel to a many combination of devices here, we can say then that the voltage across this phase is equal to the combination of the voltages of the network. For in this case, we say the voltage here is the same with the voltage here at an instant. So therefore, when you say VL is equal to VP, or the phase voltage. So VL is equal to the phase voltage. Line voltage is equal to the phase voltage. How about the current relationship? We have line current and the phase current here. So we examine line current is coming from this point here. Now, since there's a node, obviously the current that is delivered to this line here is coming from this line and this line. So we can say then that this current here is greater than the current here, or this current here. But combining the two, we have the line current here. So therefore, we say the line current is greater than the phase current. Now, up to what extent would our line current greater than the phase current? Remember the factor square root of 3. So if we say the line current would be equal to the phase current times the factor square root of 3. And of course, the phase current would be line current divided by square root of 3. So that is the formula for delta connection. Now let's go to an example. Suppose that we have a source which is in delta connection with 440 volts here, and a load also in delta connection with 50 ohms. So since this is a load, the load is represented by a resistance. Take note, in an AC system, this resistance would be an impedance. So to simplify, we represent the load as a resistance. Now, this 440 volts here is obviously the phase voltage. So right away, we can say that the phase voltage of our source is 440 volts. Now, since in delta connection, we know that the line voltage is equal to the phase voltage. So therefore, our line voltage is 440 volts. Now take note, if a generator generates 440 volts at the line, how much voltage would now be delivered to the load? So exactly, if we have 440 volts here, that would also be the same here. We have line voltage is equal to 440 volts. And likewise, since this is in delta, we know that in delta connection, the line voltage is equal to the phase voltage. So we say 440 volts. Next is our phase current. Line current and phase current here is not given. Line current and phase current here is not also given. But we can make use of what is given here, which is 50 ohms. So if we have a phase voltage of 440 volts, so we should also have a 440 volts here, since this is in three-phase configuration and they are identical. So we can solve for the phase current across this phase here, since 50 ohms is given. We can say that phase current would be equal to the phase voltage divided by R, or this is from Ohm's law, I is equal to V over R. So substituting the values, we have 440 divided by 50, we have 8.8 amperes. So the phase current here is 8.8 amperes. Next, if we have phase current, we can now solve for line current. Now in delta connection, we know that line current is phase current times square root of 3. Substituting the values, we have phase current is 8.8 times square root of 3. Line current would then be 15.24 amperes. Now remember, if the line current that is delivered to this load is 15.24 amperes, how much then is the line that it comes from our source? Of course, since 15.24 amperes is delivered here, so therefore it is coming from our source, which is also giving 15.24 amperes. So therefore the load or the line current is 15.24, and since this is in delta, of course it is obviously the same as this one, but if we will try to solve it, line current divided by square root of 3, that would give us 8.8 amperes. Now that's our answer. Now how do we solve for power? From the general power formula, we have power is equal to voltage times current. In this system, since there are phases, if we consider the total power, we will be needing the total voltage and the total current. Now also, power is the sum of individual powers, so the power of this phase plus this phase and plus this phase would be the total power. So thus the formula is PT is equal to P1 plus P2 plus P3, and so on and so forth. So since there are 3, we say P1 plus P2 plus P3. So there are two formulas that we'll be considering here. For an apparent power, apparent is the combination of reactive and resistive loads. Total power would be the line current, line voltage times the line current times square root of 3. So if we consider the line voltage and line current, we need to add square root of 3. To consider each phase, we would say that power 1 plus power 2 plus power 3. But how will we solve for each of the power here? We say the phase voltage times the phase current times 3, because each of the powers here are the same, so that is why it's times 3. So instead of writing Vp times Ip plus Vp times Ip plus Vp plus Ip, so we say Vp times Ip times 3, because there are 3 phases here. Now going back, now for the true power, we say line voltage times line current times square root of 3 times the power factor. That would be the watts, or the true power, or the real power. Or we can say, using this formula, phase voltage times phase current times 3 times power factor. Usually power factor comes from 0 to 1. Most power factors are at 0.8. Now going back to our problem, how do we solve for the power of our system? We say the total power would be the line voltage times line current times square root of 3. So the line voltage is 440 volts times the line current is 15.24 amperes times square root of 3, we have 11.614 kVA. Take note, it is the unit is kVA because it is an apparent power. Now, how about the other formula? Total power is the phase voltage times phase current times 3. So we say 440 times 8.8 times 3 would be 11.616 kilovolt ampere or kVA. Notice the difference because of the rounding off of numbers. Now, if the source delivers 11.614 kilovolt amperes, that would be the same power that is used on the load side. Now for our sample problem, pause this video and try to solve it on your own, and resume the video to reveal the answer and the solution. Okay, here's the answer. Check your work if we have the same answers. If not, try to check your work. Leave a comment if there's something that bothers you. Now for additional exercise, I need you to answer this system. Y source and delta load given a 440 volts and 10 amperes here. That's it. Thank you for watching. If you like the video, please subscribe.